In this lecture, I'm going to discuss the properties of sound waves. Sound waves are longitudinal mechanical waves that can travel in solids, liquids, or gases. And unlike the previously discussed mechanical waves in strings or ropes, sound waves are three-dimensional waves, meaning that they can travel in all directions in a medium. Let's consider a point sound source S, which emits sound waves. So here, you're looking at a cross-section of the waves as they propagate away from the sound source. And so the sound waves look like concentric circles. So those are spherical surfaces. And those spherical surfaces are called wave fronts. So wave fronts are surfaces along which the particle oscillations of the medium have same values. And the direction of propagation of the waves is indicated by those rays. So in this case, the sound source emits sound waves which propagate away from the sound source. The rays, again, indicate the direction of propagation of the wave fronts, and then the two-sided arrows here indicate the direction of oscillations of the particles in the medium. As the wave fronts propagate away from the source, the radius of the curvature of each wave front is going to become larger, and so eventually far away from the source, these wave fronts can be approximated with straight parallel surfaces. Let's talk about the speed of sound. So the speed of sound can be determined in two different ways. First is the very well-known relationship between speed, wavelength of a sound wave, and the frequency of a sound wave, and that would be that v is equal to lambda times f. So this is the speed determined from the wave properties of sound. So determined from wave properties. However, the speed of sound can be determined from the mechanical properties of the medium, just like we did for a string, for the speed of a wave in a string. For a string, we know that the speed of the wave is determined as the square root of the tension in the string divided by the linear mass density of the string. So we have an elastic property associated with the calculation, which comes from the tension, and then we have inertial property, which is encoded in the linear mass density with the mass of the string. So by analogy, I can derive similar expression for sound waves in a medium. For a sound wave, the elastic property of the medium is given through the bulk modulus B. And the units for the bulk modulus are newtons per meter squared. And then the second quantity that is the inertial property of the medium is just the density of the medium. So rho is the density. The bulk modulus is defined as the negative of the ratio of change in pressure in a small element of the medium divided by the fractional change in volume of that same element. And so the change in pressure and the change in volume are always opposite by sign, and so as a result, the bulk modulus is always a positive number. So let's explain the reasoning for the opposite signs of change in pressure and change in volume for the medium when a sound wave passes through it. Let's consider a pipe in which we have some gas, and the sound wave propagates in that gas. So the propagation is the result of mechanical interaction between the molecules of the gas. So the oscillations of the molecules will be parallel to the direction of propagation of the wave. And so since these molecules are oscillating back and forth, they will be mechanically colliding with other molecules. And so these oscillations are periodic, and the result of those periodic oscillations is the creation of regions with higher density of molecules and regions with lower density of molecules. And so, for example, let's say this is a region where the molecules are with high density, and so this is known as compression. And then we have region where we have much smaller density of the molecules, and so this region is known as rarefaction, or also expansion. So again, we have two regions as the wave passes through the medium. We have regions where we have higher density of air molecules or gas molecules, so those are known as compressions. And then we have areas or regions where we have less density of the molecules. Those are called rarefactions or expansions. And so this is a periodic phenomenon. So here, after this rarefaction, we have another compression region, and then after that we have another rarefaction region, and so on and so forth. So that means, looking at the picture here, that we have regions with higher pressure of the gas, so those are the compressions, and then we have regions with lower pressure of the gas, those are the rarefactions. And so if I look at a certain element of the gas, let's mark it with red like so. As the wave passes through this element, there will be instances when we have higher concentration of molecules, so high pressure, and then we have instances when we have lower concentration of molecules or lower pressure. And so I can calculate the change in pressure of that gas element with time. But as the pressure changes, so would be the effective volume of this element. So the volume will either, the fractional volume, so the volume will be either slightly increased or slightly decreased. And so when the pressure is high, the molecules are, we have a compression, so that means that the volume decreases a little bit. And when the pressure is low, when we have an expansion or rarefaction, the volume increases a little bit. And so when we have higher pressure, we get, when the pressure increases, the change in pressure delta P is positive, and the change in volume delta V is negative. And the opposite is also true. When the pressure is lower, delta P is negative, but then the change in volume is positive, delta V. So as a result, the two compensate each other in sign, and the bulk modulus is a positive number. And so one more time, the bulk modulus is a quantity that depends on the change in pressure in a gas element as the sound wave passes through that element, and the fractional change of the volume of that element due to the change in pressure. So the bulk modulus will depend, and also the density, of course, of the medium will depend on temperature. As we know, when temperatures are higher, molecules of gases, for example, move faster. And so that means that a sound wave will propagate quicker compared to the same gas when the temperature is lower and the molecules of the gas move slower. And so the speed of sound in air, at standard conditions, which means 20 degrees Celsius, normal atmospheric pressure, and 3.5% humidity, is equal to 343 meters per second. So 343 meters per second. For reference of speed of sound in various media, you can use table 17-1 in the textbook, where you have the speed of sound in several different gases, in several different liquids, and also in several different solids. From the table, you would see that the speed of sound in gases is the slowest. It's about 10 times. It's about 5 times faster in various liquids compared to the gases shown in the table, and then it's about 20 times faster in solids compared to gases. And so the reason for that is, of course, the spaces between molecules or atoms of the medium. For gases in general, the spacing is substantial, and so it takes longer for molecules to interact with other molecules, to collide with them, so that the sound waves propagates through the medium. In liquids, the space between the molecules is much smaller, so it takes much less time for molecules to interact with each other. And of course, for solids, due to the structure of the material, where the atoms and molecules are fixed in place, the interactions happen much quicker, and therefore the speed of sound in solids is so much faster than gases and also liquids. So when sound waves are generated in a medium, those waves will propagate in space. And so if we look at a tube in which we have some gas confined, let's say air, if I have a source of oscillations here, source that creates these disturbances in the gas, which result in compressions of the molecules and then rarefactions of the molecules, or expansions of the molecules, this source, because of its periodic nature of the excitations of these molecules, will create this traveling or moving pattern of compressions and rarefactions down the tube. And so a wave is generated that travels down the tube, so this is a traveling sound wave. If you look at a single element in this gas, when the wave passes through that element oscillates back and forth. And so this oscillation happens with a certain amplitude. Let's call this amplitude Sm. And so this is a periodic motion, so therefore I can describe the wave function of the sound wave by multiplying the amplitude of oscillations by a periodic function that will that can describe the periodic nature of the wave. Since the source of the wave is a constant source, meaning it oscillates the same way all the time, so it has the same frequency of oscillation, the same amplitude of oscillation. That means that the wave itself will oscillate in a simple harmonic fashion. And so therefore I can describe the wave the following way. So the wave function, which also describes the displacement, I will write as S of x and t, and that's the product of the amplitude Sm and a periodic function which will be cosine of kx minus omega t. We are already familiar with the parameters of such a function, namely k is the wave number, and that is equal to 2 pi divided by the wavelength of the sound wave. So again, that was the number of wavelengths that fit a unit length, let's say 1 meter. We have the angular frequency omega, which is equal to the product of 2 pi and the frequency of the sound wave. And now we have a new quantity that we haven't seen before, and that is the pressure or the pressure change of the sound wave. So the pressure change delta P is the product of the pressure amplitude delta Pm times sine of kx minus omega t. So as we know, when sound waves propagate in a medium, there is a pressure change due to the alteration of compressions and rarefactions or expansions in the medium. Okay, so this essentially is similar concept to what transverse velocity was for a string element when a wave passes through that element in a string. So, but here, since the gas molecules do not move all in the same direction as the wave propagates, they still have random direction of motion, but as a whole, they either are going to end up in a compression or in a rarefaction. It makes more sense to talk about pressure amplitude rather than transverse velocity or longitudinal velocity or whatever you want to call it. But it has the same meaning as the transverse velocity for transverse waves. And so it turns out that the pressure amplitude delta Pm is equal to the product of the speed of the sound in that particular medium times the density of the medium times the angular frequency of the wave times the amplitude of the wave. And so this last relationship here gives us the relationship between the pressure amplitude and the displacement amplitude of a element in the gas or the medium. So sound waves are periodic waves, and when two periodic waves meet at the same point in space, they undergo interference. And so now let's discuss how the interference of sound waves work. Let's consider two sound sources, point sound sources, S1 and S2, that are located along a straight line like so, above each other. And so those two sound sources emit sound wave. Both sound sources emit the exact same wave. So that means the same amplitude, the same wavelength, except for sound source S2 emits a wave that has a phase angle phi that is not equal to 0. So the phase difference is phi between the two sound waves. So the wave emitted by the source S1 is equal to Sm cosine of kx minus omega t. And the wave emitted by S2 is Sm cosine of kx minus omega t plus phi. So we know from the previous chapter that the resultant wave, when the two waves interfere with each other at point P, is given by S prime equal to 2 times Sm cosine of phi over 2 times cosine of kx minus omega t plus phi over 2. So this again is an equation of a traveling wave, and the amplitude of that traveling wave, Sm prime, is just the magnitude of 2Sm times cosine of phi over 2. So the value of phi determines whether this amplitude will be maximum, 0, or somewhere in between. So in other words, the value of the phase angle phi determines whether at point P the two waves will interfere in constructive interference, destructive interference, or intermediate interference. And so then the factor that determines how these two waves will interfere at point P is actually the length of path that the two waves will travel to point P. So that means that there has to be a relationship between those two paths and the phase angle phi. So let's see what that relationship is. So before I do talk about the relationship between lengths of paths and the phase angle, just to describe visually what fully destructive and fully constructive interference means, here is an example of a fully destructive interference. So that means that the two waves meet exactly out of phase. Or in other words, when the two waves reach point P, they both will have opposite phases. And so that means that the two waves will cancel each other out and there will be no amplitude of the resultant wave at point P. So for example, if the difference of paths is equal to 2.5 wavelengths, the two waves will meet at point P exactly out of phase and they will cancel each other out. Fully constructive interference occurs when the two waves meet at point P exactly in phase. For example, if the difference in paths is equal to 2 times the wavelength of the waves. So then we have fully constructive interference, and we will have double the amplitude of the waves for the resultant wave at point P. And so now let's see how the phase angle and the path lengths are related to each other for those two conditions to occur. So since the two waves must travel in space between their sources S1 and S2 and point P, they will obviously they will travel different lengths of paths. And so depending on the length of those two paths, it's possible that the two waves will end up at point P exactly in phase, which will result in constructive interference. And of course, there's also the possibility that they will meet at point P exactly out of phase when we have destructive interference. So an important parameter here is the difference in paths between the two waves. So delta L, which is the magnitude of L2 minus L1, is an important parameter in the calculation. So since we're dealing with periodic waves here, we know that one wavelength of the wave corresponds to a phase of 2 pi difference. So that means that I can create a ratio such as phi divided by 2 pi, and that will also correspond to the ratio of the difference in path length delta L over lambda. So the wavelength is 2 pi periodic, and so I can relate that with this difference in paths and the phase angle or the phase difference between the two waves. And so if I rearrange the terms, I end up with this expression here that relates the phase angle and the difference in paths delta L with the wavelength of the wave for a condition of interference. So let's go back to the expression for the amplitude of the resultant wave of those two sound waves interfering with each other. That depends on cosine of phi over 2. And so when is this equal to the maximum possible value of 2 times Sm? Well, that's going to happen only when phi is equal to an integer number times 2 pi, since cosine is a periodic function. And so the integer number m varies from 0 to infinity, so 0, 1, 2, 3, and so on and so forth. So if I apply this to the expression from the previous page, phi equal to delta L over lambda times 2 pi, it is clear that delta L over lambda would be equal to 0, 1, 2, and so on and so forth. So here are my two conditions for constructive interference. Either phi is equal to an integer number times 2 pi, or delta L divided by lambda is 0, 1, 2, and so on and so forth. So when determining whether two waves will create constructive interference at a point in space, those two conditions can be applied to check for that whether the interference is constructive or not. Similarly, this amplitude is equal to 0, meaning fully destructive interference, and there is a typo right here, so let's fix that. Fully destructive interference occurs when phi is equal to an odd multiple of pi. So 2m plus 1 times pi, where m is equal to 0, 1, 2, 3, and so on and so forth. And then again, from the relationship between phi and delta L, we end up with delta L divided by lambda equal to 0.5, 1.5, 2.5, and so forth and so on. So those two conditions here can be used to determine whether, when the two waves meet at a point in space, they undergo fully destructive interference. Let's shift our attention now to some macroscopic properties of sound waves. So first, let's talk about intensity and sound level. Intensity is defined as the average rate per unit area with which energy is transferred by the wave through or onto a surface. And so this is written as the intensity I is equal to power divided by the area of that surface. The intensity is also related to the displacement amplitude Sm of the sound wave by I equal to 1/2 rho, which is the density of the medium, times v, which is the speed of sound in that medium, omega squared, that's the angular frequency of the wave, and Sm squared, which is the displacement amplitude of the wave. So in this relationship, we see the dependence on some physical parameters of the wave, such as the density of the medium and the speed of the wave in the medium, and then some wave properties, which are the angular frequency and the displacement amplitude. So this expression is very similar to the expression that we got for the average power transmitted by a wave in a string. However, this is for a sound wave, and this is the intensity of the sound wave. So since the intensity was defined as power divided by surface area, and sound waves are spherical, three-dimensional spherical waves, then the intensity can be written as the power divided by the surface area of a sphere. And the sound source S emits the sound waves uniformly in all directions. And the sound waves are emitted in all directions with equal intensity. So then this form of the equation for intensity allows me to compare sound intensities at different distances from the power source or from the sound source. And as you can see, the dependence is as the inverse of the square to the distance, which means that when I double the distance from the sound source, I am dividing the intensity by 4. If I reduce the distance 2 times, then I am multiplying the intensity by 4. So this is not a linear dependence. The relationship between intensity and distance from the source is not a linear dependence. It's not a linear relationship. So hearing in humans is based on the reaction of the eardrums to the displacement amplitude of the waves that interact with the eardrums. And so it turns out that the range of displacement amplitudes that the human ear can hear or can register is pretty wide. The range of displacement amplitudes that the human ear can register is from 10 to the negative 11th meters to 10 to the negative 5th meters. And so the ratio of those two is 10 to the 6th. But if you remember from previous slides, the intensity is proportional to the amplitude to the second power, which means that human hearing can register within a range of 10 to the 12th. So our range of hearing is actually enormous. We can hear a giant number of intensities. And so because of that, we must use a different system of that allows us to compare intensities, and that is the decibel system. And so the decibel system is based on the concept of logarithm. So if I have two variables, y and x, I can write the relationship between the two using a logarithm of base 10, and the relationship would be y is equal to log x. So a property of logarithms is that if I multiply x by 10, then y will be equal to log times 10 to log of 10x, which also can be written as log of 10 plus log of x, and log of 10 is equal to 1. And so we have 1 plus log of x, or that is 1 plus y. Similarly, I can multiply x by 100, and so y is equal to log of 100x. That is equal to log of 10 to the second power times x, which is equal to log of 10 to the second power plus log of x. Finally, this is equal to 2 times, or is equal to 2 plus log of x, or that is equal to 2 plus y. So if I do the same thing, but instead of multiplying x by 10, I multiply it by 10 to the 12th, y is equal to log of 10 to the 12th x will basically become 12 plus y. So then that means that I can use this representation to work with such a giant range of intensities that the human ear can hear. And then instead of speaking of intensity I of a sound wave, it's much more convenient to speak of the sound level of a sound wave. And this sound level, beta, is defined as 10 decibels times log of I divided by I0. And I0 is a reference intensity level, which very typically is the lowest audible intensity for the human ear, which is 10 to the negative 12 watts per square meter. And so I can compare the intensity level of a sound source to the lowest possible intensity level that the human ear can register, or it's also this definition here is also useful to compare intensity levels between two sources, one unknown and another source that has a known intensity. Let's see what happens for various values of I and I0. So first let's look at what we get for beta, the sound level when the two intensities are equal. So when I is equal to I0, we get beta is equal to 10 decibels log of 1, which is equal to 0. So the sound level corresponds to 0 decibels. Or in other words, we can't hear that sound because the human ear can't register that. Okay, now let's look at the next relationship. Let's say I is equal to 10 times I0. From that, beta is equal to 10 decibels log of 10, and that is equal to 10 decibels. So the sound level is 10 decibels. Okay, let's see what happens when the relationship is I is equal to 100 times I0. From that we get that beta is equal to 10 decibels log of 100, and so that is 20 decibels. So what we see here is that for a source with intensity equal to 100 times the reference level, we get sound level of 20 decibels. So then if I consider a sound level that is equal to 50 decibels, that means that the intensity of a sound source is equal to 10 to the 5th times the reference intensity, the hearing intensity threshold. So 10 to the negative 12 watts per meter squared. Here are some values for sound levels of different sources of sound. So rustle of leaves, 10 decibels. That means that this is 10 times the threshold of hearing. Conversation is 60 decibels. That means 10 to the 6th hearing threshold. Rock concert is 110 decibels, so that is 10 to the 11th times the hearing threshold intensity. The pain threshold is 120 decibels, so that is 10 to the 12th times the hearing threshold intensity, and jet engine is 130 decibels. In the previous lecture, I talked about sound waves, not sound waves, but mechanical waves propagating in strings and creating standing waves patterns. So now let's discuss the same concept, but in terms of sound waves. So standing wave patterns are created in musical instruments typically. And so we're going to discuss wind instruments. And we have two possibilities for a wind instrument where a sound wave can create musical sounds. So that would be a pipe with two open ends, or a pipe where one end is closed and the other end is opened. So those are the two possibilities. Due to the nature of how musical sounds can be created in those two situations, we will end up with two different relationships for the wavelengths and the frequencies of the harmonics that can be created in those wind instruments. So first I will start with a pipe with two open ends. So here is my pipe with two open ends. The length of the pipe will be L. So what I want to figure out is what's the relationship between the wavelength of a sound wave generated in or propagating in this pipe and the length of the pipe. And of course, also I want to figure out what's the frequency of such wave. And as we know, musical sounds can be created by waves that can generate standing wave patterns, in this case in the pipe. And so I want to see if I can figure out a general relationship that can calculate any wavelength and any frequency of a wave that can generate a standing wave pattern in a pipe with two open ends. So the first condition for a musical sound to be produced in this pipe is that at both open ends I have an antinode. So I want an antinode here and here. So then I must use that condition to come up with a wave pattern that is a standing wave pattern, and that would look something like this. The longest wavelength that will have antinodes on both sides when a standing wave is generated will have one node in the middle, and then it will look like this. Okay, so as you can see from the pattern, each branch is lambda over 4. And so from here I can say that lambda 1, which is the wavelength of the first harmonic here, is, so 2 times lambda 1 divided by 4 is equal to L, or in other words, lambda 1 is equal to 2 times L. So the wavelength of the first harmonic, the longest possible wavelength that can fit in the pipe so that the conditions for antinodes on both ends is satisfied, is twice the length of the pipe. So then I can use the relationship between the speed of sound in air, the wavelength, and the frequency to figure out what the frequency of the first harmonic would be. And so V of sound is equal to lambda 1 times F1. So F1 will be equal to V of sound divided by 2 times L. And so this here is the first harmonic. So let's do the second and the third harmonic, and then I will write a generalized expression for the wavelengths and the frequencies. So for the second harmonic, I must fit a wave with shorter wavelength compared to the first harmonic, but again I want antinodes at both open ends. So that means that I will have 2 nodes inside the pipe and 2 antinodes on both open ends. And so the standing wave pattern inside the pipe looks like so. Alright, so let's see what the wavelengths corresponding to those branches are. So this branch here is quarter wavelength long, the one there also quarter wavelength long. Then we have another branch which is half of a wavelength, another one that's another half, and then here we have a quarter wavelength and another quarter wavelength. So then that means that I have 2 times lambda over 4 plus lambda over 2 is equal to L. So that is basically tells us that lambda 2 is equal to L. So the wavelength of the second harmonic is equal to the length of the pipe. And so if I apply V of sound is equal to lambda 2 times F2, I end up with F2 is equal to V of sound divided by L. And so I will also rewrite this as 2 times V of sound divided by 2L. Now let's do the third harmonic. So for the third harmonic, we have now 3 nodes inside the pipe and antinodes on each open end. So let's see what the branches are in terms of wavelength. So we have lambda over 4, lambda over 2, lambda over 2, lambda over 4. So then that means we have 2 times lambda over 4 plus 2 times lambda over 2 is equal to the length of the pipe. And so indexing lambda for the third harmonic, I get that lambda 3 is equal to 2 times L divided by 3. And again, using that, the speed of sound in air is equal to lambda 3 times F3. I can say that F3 is equal to 3 times V of sound divided by 2L. And so now I have a general rule, or I have enough relationships to look at between lambda and L and F and L to write a general relationship that calculates any wavelength and any frequency that can create a standing wave in such pipe. And so when the pipe has 2 open ends, the frequency is calculated as n times the speed of sound in air divided by 2L, where n is 1, 2, 3, and so on and so forth. And the wavelength is calculated as lambda n is 2 times L divided by n, where n is 1, 2, 3, 4, and so on and so forth. So again, just to have it here together on the slide, V is Vs, and that is the speed of sound in air. So if no specific value for the speed of sound in air is presented in a problem, you would always assume that that is the speed at standard conditions, or in other words, 343 meters per second. So notice that those relationships here look exactly the same as the relationships we got for a standing wave in a string with both ends fixed. So even though here we're talking about sound wave in a pipe. Now let's discuss standing waves and wind instruments with one open end. So for simplicity, again, I'm going to discuss a simple pipe which has one end closed. So the requirement here is that at the open end there is an antinode, and then at the closed end there is a node. So let's see what the first harmonic looks like. So here is the pipe with one open end and one closed end. We have a node at the closed end, and so the wave that has the longest wavelength that can create a standing wave pattern in this pipe looks like so. So the branch here is lambda over 4, and this other branch is also lambda over 4. So this means that lambda over 4 is equal to L. So a quarter of the wavelength fits the length of the pipe. And so then from here, lambda 1 is equal to 4 times L. So the wavelength of the first harmonic is equal to 4 times the length of the pipe. So then from the relationship between the speed of sound in air, the wavelength, and the frequency, I get that the frequency would be equal to Vs divided by 4L. So already we see that there is a significant difference between the first harmonic wavelength and frequency for a pipe with one closed end and a pipe with both ends open. Let's do the second harmonic now. So here is my pipe. One end is closed, the other one is open. So again, I must have a node right here, and then I will have another node in the middle of the pipe. So then the standing wave pattern will look like so. And so this branch here is lambda over 2, and this one is lambda over 2, and here we have lambda over 4. So then that means that lambda over 2 plus lambda over 4 will be equal to the length of the pipe, or 3/4 lambda is equal to the length of the pipe. Finally, lambda 3 is equal to 4L divided by 3. In this lecture, so here, we noticed that there is a bit of a discrepancy in the sequence of harmonics compared to the case with two open ends. So the first harmonic, we had that the wavelength is equal to 4 times the length of the pipe. And then what I called the second harmonic, the wavelength is equal to 4 times the length of the pipe divided by 3. So there is no wavelength that is equal to 4 times the length of the pipe divided by 2. And so we will see for the next harmonic that the wavelength will be equal to 4 times the length of the pipe divided by 5. And so essentially, we are missing all the even numbered denominators in this sequence. We only have the odd numbered denominators. And so because of that, the harmonics will be labeled differently compared to two open ends. So we have lambda 1, lambda 3, lambda 5, lambda 7, and so on and so forth. And because of that, the harmonics will be called the first harmonic, the third harmonic, the fifth harmonic, the seventh harmonic, and so on and so forth. So my derivation that I initially labeled the second harmonic will need to be renamed, and the name will be the third harmonic. So now let's figure out the frequency that corresponds to this wavelength. And so the frequency that corresponds to the third harmonic is equal to 3 times the speed of sound in air divided by 4 times the length of the pipe. Let's do the next harmonic, and then I will talk about the general rule for calculating wavelengths and frequencies of the waves that can create standing wave pattern in a pipe with one end closed. So here is the next wave that can generate standing wave pattern in the pipe. We have a node at the closed end, an antinode at the opened end, and we have 2 other nodes inside the pipe. So here we have lambda over 2, lambda over 2, and lambda over 4. And so 2 times lambda over 2 plus lambda over 4 is equal to the length of the pipe. Or in other words, lambda 5 is equal to 4L divided by 5. And so because the denominator is equal to 5, using the convention from before, we name this the fifth harmonic. So again, for waves that can create standing wave pattern in a pipe with one end closed and one end opened, we only have odd numbered harmonics. So first, third, fifth, seventh, so on and so forth. Okay, now let's see what's the general formula for the wavelengths and for the frequencies of standing waves created in a one open end pipe. So here is the formula for the frequencies. So the frequencies are equal to n times v divided by 4L, where n is equal to 1, 3, 5, so on and so forth. And let me add the formula for the wavelength. So lambda n is equal to 4L divided by n, where n is equal to 1, 3, 5, and so on and so forth. And here again, v is the speed of sound in air. And again, if the problem does not specify the speed of sound in air, you would assume that that would be 343 meters per second. Let's now talk about the phenomenon of beats. So beats is the result of two waves with frequencies that have similar values interfering with each other. And the resultant wave is another periodic wave which will have frequency, which will have intensity that will vary with a frequency equal to the beat frequency. So here are the two periodic sound waves that will interfere with each other. When they interfere, they create a wave that has varying amplitude, and this amplitude varies with frequency, which we call the beat frequency, and that is calculated as the difference between the frequencies of the two interfering waves. Obviously, when you calculate the beat frequency, since it has to be a positive number, you would subtract the smaller frequency from the larger frequency. So, for example, if you have two waves, one with frequency f1 equal to 350 hertz, and another one with frequency f2 equal to 352 hertz, then the beat frequency will be 352 minus 350, and that will be equal to 2 hertz. So for the resultant wave, when those two waves interfere with each other, the amplitude of the wave will change with a frequency of 2 hertz. So you're going to get maximum intensity of the sound, then minimum intensity, then maximum again, and this will be periodic with frequency of 2 hertz. So the last concept that I want to discuss with you is Doppler effect. So Doppler effect is the change in the observed frequency of a wave when the source or the detector, or in other words the observer, moves relative to the transmitting medium, for example air. So for sound, the observed frequency f prime is given in terms of the source frequency f by the general Doppler effect formula. So f prime is equal to f times v plus or minus vd divided by v plus or minus vs, where vd is the speed of the detector or observer. So vd is speed of detector or observer, and Vs is the speed of the source. V is speed of sound in air. So depending on how the source of the sound and the detector move with respect to each other, with respect to the medium in which the sound wave is transmitting, the detector will detect different frequency than the frequency which the source emits. So let's explain that a little bit. So on the left here, we have a situation where the detector is moving and the source is stationary. Specifically here, the detector is moving towards the source. So the source emits sound waves, they propagate away from the source. So the sound waves travel towards the detector. And of course, the detector is moving towards the source. So the source emits these waves with certain frequency f. And so then the frequency that the detector hears is the frequency with which those sound waves are registered by the detector. But so since the detector is moving towards the source, the frequency with which the detector detects these sound waves is actually higher than the frequency with which the source emits the sound waves. So when the detector moves towards the source, the frequency that the detector hears is higher. Now, if the detector was moving away from the source, then again the frequency that the detector would register would depend on how frequently the sound waves reach the detector. And so since the detector is moving away, the frequency of detection will be lower than the actual frequency of the sound waves emitted by the source. And so then I can modify the general Doppler effect formula to account for the direction in which the detector moves with respect to the source when the source is stationary. So first let's write down the Doppler effect formula for detector moving towards the source and the source is stationary. The frequency that the detector will detect, f prime, is equal to the frequency emitted by the source, f, times v, the speed of sound, plus vd, the speed of the detector, divided by v, which is the speed of sound. As expected, the frequency detected by the detector, f prime, is greater than the frequency emitted by the source. For a detector moving away from the source when the source is stationary, the frequency that the detector will register, f prime, is equal to f, v minus vd divided by v. So v source again is 0. So as expected, the frequency detected by the detector is smaller than the frequency emitted by the sound source because the detector is moving away. So the minus sign means the detector is moving away, and the plus sign means the detector is moving towards. Now let's reverse the rows here and have the detector stationary and the source moving towards the detector. So on the right here we have a drawing that shows a situation where the detector is stationary and the source is moving towards the detector. So what happens is the wavelength of the waves emitted by the source decreases. So which is a result which results in increase of the frequency of those sound waves. So the detector will register a frequency higher than the frequency of the sound emitted by the source. So let's look at the formulas that describe that situation. So again, we have two possibilities. What I just talked about, meaning the source moving towards the detector, and the other possibility is the source moving away from the detector, and the detector in both cases is stationary. So let's first discuss the situation where the source is moving towards the detector, and again the detector is stationary. The frequency registered by the detector, f prime, is equal to the frequency emitted by the source, f times the speed of sound in air divided by the difference between the speed of sound in air and the speed of the source. And so, again, because the wavelengths get shorter, since the speed of sound in air is fixed, the frequencies must get higher or increase, and so that relationship is correct. Now let's look at the other possibility where the source is moving away from the detector. So when the source is moving away from the detector, the frequency detected by the detector, f prime, is smaller than the frequency emitted by the source, so that means v divided by v plus vs, and again the detector is stationary, so vd is equal to 0. So now let's look again at the general Doppler effect formula. So the frequency registered by the detector f prime is equal to the frequency emitted by the source times v plus or minus vd divided by v plus or minus vs. So this formula can be modified for any situation that we've discussed already. For example, if the detector is stationary, then vd becomes 0. And then depending on whether the source is moving away or towards the detector, you're going to select the signs here plus or minus accordingly. Similarly, if the source is stationary, Vs is 0, and then depending on whether the detector is moving away or towards the source, you would select the signs plus or minus here accordingly. So the general rule of how to apply the signs in the general Doppler effect formula is when the detector is moving away from the source, we select the minus sign, or if it's moving towards the source, we take the plus sign, and then if the source is moving away from the detector, we take the plus sign, and when the source is moving towards the detector, we take the minus sign. And so if both are moving at the same time, we again select the signs according to those two diagrams, depending on how the two are moving. So for example, if the detector is moving towards the source, we take the plus sign, but if the source at the same time is moving away from the detector, we take the plus sign here as well.